let's say you're measuring to figure out how the centripetal force affects the velocity of something, and you're using constants where your radius is 1.5 meters and your mass is 2 kilograms. So you get that data in there, and you're going to highlight what you have here, and you'll go up to Insert, and when you do that, you'll go down to Chart. Now it'll appear with a chart. Sometimes it is in scatter platform, and sometimes it is in something else. And so if it's in something else, you'll go all the way to the top and you'll move it into a scatter instead of whatever else it shows up as. Sometimes it shows up as those other things. But because we know that this is a square root relationship here, I know it looks a little bit linear, but according to the equation, it's a square root relationship. So we're going to linearize the graph. And we're going to type in the square root of our centripetal force here, just for our title. And we'll do something with that in a moment. The velocity on the y-axis is going to stay the same. So we highlight what we have here, and we copy it, and we paste it down here. Now, here's where the magic comes in. We want to change our horizontal axis into the square root of centripetal force. So you're going to type equals, and then SQRT, and you'll see it pop up. You'll click on that. And it's a function, so then you'll click on the box that you want to take the square root of, and then put the parentheses in and hit enter. And so you do that there, but the thing that's nice is you don't have to go and do that on all of them. Click on that circle and drag it down, and it'll do that for the numbers that are below it. And it'll just keep that same correlation in reference to where that first one was. So now we have the square root of centripetal force on the x-axis, and we'll get another chart, and it looks like that. So that now is a linearized graph. I know the first one looked semi-linear, but we know that it's square root. And you'll get your scatter plot, but then you're going to go to the series. You'll go Customize, then Series, and go on down, and you'll say that you'll add a trend line. So you'll click on that trend line box. You can see the line up here, and then continue down in the trend line area, and at Label, go to Use Equation. So it gives you that equation that's up there. And so now you have the slope from that equation as well. So here's where the fun stuff comes in, because we're using the equation that says FC equals mv squared over r. And we were in control of changing our centripetal force. So this is our independent variable. And we were measuring the velocity there, that's our dependent variable. So we need to get this rearranged into a v equals equation. So we're going to solve for v here. And we'll multiply both sides by r. So we get it off the bottom. We're trying to get v by itself. It cancels out over here. We'll divide both sides by m. So when we do that, we end up with v squared equals r times fc over m. And it's possible to manipulate the y-axis variable, but it is not as easy to do so when you start adding in error bars. And so we want to get this to strictly v equals. We'll take the square root of both sides. So we'll have v is equal to the square root of r times our centripetal force over our mass. Well, now we can do something with that. We have our dependent variable here. We have our independent variable here that we were changing, and we can put that into y equals mx plus b format. So if we put our boxes here, we have y equals mx plus our b. In this case, our b is going to be 0, but both of those things, all these things are in here. So we have our dependent variable here, which is our v. We have our independent variable here, which is what we're changing and whatever's happening to it. So because it's inside of that square root, our independent variable that we're going to linearize with now is the square root of our centripetal force. And then everything else is our slope. So in this situation, we've got r over m, and we're taking the square root of that, r over m, like this. So what we did is with the graph, we were able to get a numerical slope. And we got that numerical slope. The slope from our graphed data was 0.873. And then we can compare that to what happens here. Well, we know that our radius was 1.5 meters and our mass was 2.0 kilograms. So we can say the square root of r over m, square root, our radius was 1.5 meters divided by our mass of 2.0 kilograms. So it's the square root of 0.75, which ends up giving us 0.866. And while not absolutely exact, when we get into error bars, you'll see where that part goes. But this and this are pretty much aligned with each other. They both round to 8.7, which helps us justify that the results we got compared to the things that we know about what we held constant both fall within the same range.